This session and the next is, these are the last two sessions in the theory part of this chapter. It's been a long chapter, about 50 pages. So probably at the end of the second session, I still have a little bit of board. So I might introduce a selection of computer science type text, computer theory, that I may use in future courses. Some I'll definitely use, others I'm not quite sure yet. There may be too much overlap with earlier computer theory texts. Also, I discovered that my camera has been slightly zoomed for quite a while, so I put it back to the default unzoomed position, and as a consequence of that, the camera is now a little closer physically to me. I don't know if that's going to have much effect or not. Alright, so this and next session we will do the fourth and fifth examples of using the pumping lemma as part of a proof by contradiction that certain language is not regular. So we'll do the fourth and fifth along the same lines. So you're getting quite familiar with it. But each time there's a twist. Each time there's something a little different. Now, Sipser says when you're choosing your string S, that you will try to prove does not belong to the language. You're trying to find a counterexample, a contradiction. You choose wisely. Try to choose an example that you really think is characteristic of some string that would not be a member of a regular language. Now that's a bit vague. It's sort of hard to make it more explicit. But go looking for examples of your strings that are more likely to not have the property that would make them members of a string that it is regular. So in other words, go looking for strings that have some kind of non-regular quality, given the definition of the language. Like I say, a bit vague. Alright, now so the fourth example, so example 1, so chapter 1.76, so the 76th thing, labelled, ID with a number in this long chapter, so 76, quite a few things. Right? Now, what's different in this particular example, oh, by the way, the grey and the black, I've just picked up what I thought was a black pen, and someone gave me a free sample which was actually grey. I mean, the actual colour of the ink is grey rather than black, where I was thinking it was just starting to dry out. But no, it's actually grey, until that dawned on me. So then I picked up another one that is black. So, after 4 months, there's still surprises. Like last night, just overnight, but just within 2 to 3 hours, I downloaded the previous days and nights filming in 2 to 3 hours. So the total upload speed to YouTube now is no longer an issue. So I'm going to have to change my website, because I was complaining earlier about the extremely slow upload times to YouTube. Well, if you do it in bulk, in parallel, you have, I mean, I opened eight YouTube windows last night, and put one video clip, each about 10-12 minutes typically, one in each window, and had 8 of them uploading at the same time in parallel to YouTube. And it works fine. So nice trick. So if any of you have suggestions on how can I speed up the pre-processing, like once I download the film from the camera to my laptop, well, say a session is about 20-30 minutes typically, and I'll split it up into 2 or 3 pieces or clips. You're clipping. So there's 2 phases in the pre-processing. One will take half an hour. That's for the whole, say, 30-minute session, and then maybe 10-20 minutes per clip. So you add that, and it's about an hour or more just in pre-processing. So I'd like to be able to cut down on that as well, if possible. So if you have any suggestions, please email me. Right. So the next example of disproving that, proving that a particular language is not regular. Now this time the difference is that the language is now unary. There's only one symbol in its alphabet. So call it 1. So here's the language, D. Here's the one symbol in the alphabet. Let's just call it 1. And the property of the strings in this language is that their length is a perfect square. So the property of W is that W is of the form 1 to the power n squared. So you've got a power to a power in a sense. Okay. So the length of these strings is n squared. Okay. So a perfect square, where n is greater or equal to 0. Okay? So D contains all strings whose length is a perfect square. Now, as usual, like the next few lines, they're the same in all these examples. So we're going to use the pumping lemma, and we'll prove that D, this language here, is not regular by using a proof by contradiction. Okay. All right. So we assume the opposite of what you're trying to prove. We're trying to prove that D is not regular. So we're going to use proof by contradiction. So we start with the opposite of what we want to prove. In other words, not regular. In other words, regular. So assume D is regular, and let little p be your pumping length as usual. That comes from the pumping lemma. And so now let's choose a string S. And this is the critical part, as usual. The critical part in the proof is your choice of S, because you're trying to show that it's impossible that S can, a pumped S. It's impossible that pumped S can belong to the language. So we'll try to show that this choice of S, when we pump it, that it cannot, the pumped S, the pumped string, cannot belong to the language D. Alright? Okay, so here's the actual choice Sipser gives. Your n here is now going to be the pumping length. Okay? So your string now is 1 to the p squared. Remember that's your shorthand. It just means you're concatenating 1 p squared times. So 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, your p squared times. Right? Now p is an integer. Right? So this S is of this form, where we're just n is p. So therefore this string S belongs to this language. So S belongs to D. You're assuming D is regular. Right? Now the size of S is obviously greater than P. Wait a minute. Or equal to P. Now wait a minute, be careful here. So if P is 0... Now p squared in general is larger than P unless P is 1. And you could have 1 to the 1 squared, which is like 1 to the 1, which is just your string is just a single 1. Yeah. Okay. So you need an equal sign here. So the size of S, the size of this, is greater or equal to P. Right? Like when P is 1, the size of this is equal to 1, so you need the equal sign here. But in general, other than that one case, the size of S is greater or equal to P. And that's a condition, that's one of the conditions for the pumping lemma applies to all those strings whose length is greater or equal to the pumping length, but we've let P be the pumping length, and that's the same P that's here. And therefore this string here is subject to the pumping lemma. In other words, you can split it up, the string S, into X, Y, Z, like 3 substrings, such that S, X, Y, Z, can be pumped. Right? That's the first condition of your pumping lemma, that X, Y to the power I, here, that this pumped string also belongs to the language, okay? Belongs to D, right? Now, as as in earlier examples, we'll just show that this pumped string here cannot belong to D. It's impossible that this belongs to D. And we don't have to go very far. Well, usually we just we just add one extra copy of Y, X, Y, Y, Z. In this case, no, it's